the atmosphere. And in the near field, right, there's a lot of dilution and transformation, and you guys have done a lot of nice work. Naomi Zimmerman is working with me right now as a postdoc, and the work that she did right down on the street there, sort of measuring, how the particles were transforming, and that's a topic that I'm interested in, and I could be talking about that today, but I'm not going to be talking specifically about that today. I'm going to be talking more about what happens as we move a little bit farther downstream. And the emissions, they float around in the atmosphere for a week or so, and they get photooxidized by atmospheric oxidants like the hydroxyl radical, ozone, and they get transformed chemically, and you make secondary aerosol. Because some of the products, the products of some of those gas phase reactions are low volatility, and they condense. So thinking about, thinking about what the connection is between here. So if you do some source testing, and my word source is cut off a little bit, but we're measuring like at the end of the tailpipe. So if you do constant volume sampling, sort of source testing, where you're sampling into that, you're sort of simulating the dilution, but really you're simulating like 1 foot downstream from the tailpipe. And I don't put 1 foot downstream. Every once in a while I'm riding my bike behind like a Volkswagen microbus. I'm being fumigated, so maybe I get a little bit of that. But most of the time, that's not where we're at. I mean, usually we're farther downstream. So thinking about how those transformations change what you're being exposed to, and understanding that is really important. So my research is sort of thinking about this, and it can be important from a toxicology perspective. Often toxicology is done with fresh emissions, but is that really representative of what you and I are breathing right now in this room? And it probably isn't. So sort of studying those transformations, and I sort of study that whole value chain, but we're going to be talking sort of about the part in the cloud today, which is this atmospheric transformation, secondary aerosol production. So that's one theme of my research, is thinking about these transformations and thinking about human exposure. Another part that I really work on is organic aerosol. So this is a pie chart of the composition of fine particulate matter, and this is from Los Angeles, measured during the CalNext study, which was a big air quality study that was done in 2010. And this isn't, it's reasonably representative, and it's broken into sort of composition. And I spent a lot of time studying this wedge, which is the organic wedge. See John there in the back, John Abbott. Arthur studies this sort of part of the puzzle a lot, and so I think about this part. That's sort of another part. So we're going to merge these two themes sort of in a second. And you can see here it's about 40%. So it's a large fraction. So where does it come from? Well, it comes from a lot of different sources. Biogenic sources that are emitting either directly primary biological material, but more often they're emitting gases that then are oxidized to form what we call secondary organic aerosol. I don't study the biogenic part of the problem much. I study more the anthropogenic, the combustion system part. That's the part that we can control if we're going to develop policies and regulations. And so, you can think about all these anthropogenic sources, the ubiquitous diesel truck, automobiles, there's a guy cooking some burgers, fires of different types, and all these systems, or combustion processes are emitting emissions into the atmosphere that are being transformed. And so studying that. And so what's the relative importance of sort of those direct particle emissions versus secondary? Right now, the current thinking, even in a lot of urban areas, that there's a lot more sort of secondary production. That's not necessarily true right next to a road, but if you sort of look at urban background sites. And so studying this sort of arrow, this kind of pink arrow, is what we're going to be studying today from gasoline vehicles. And it's important to study because models to predict this secondary organic aerosol don't work very well often. And so this is from CMAQ. So CMAQ is the model that EPA has developed that's used for a lot of regional modeling and analysis. And this is looking at predictions, and this is sort of the current sort of regulatory version of the organic aerosol mechanism. And you're like, great, our R value is 0.86, super correlated, but man, we're a factor of 5 too low. And so there's just a lot of gaps, and this talk isn't about sort of closing those gaps necessarily. We'll talk a little bit about closing those gaps. I spend a bunch of time sort of thinking about how to better model it and sort of close the gaps. But it's just to point out it's a really complicated sort of part of the fine particulate matter, and models have a hard time representing it, and these sorts of things. So sort of studying that kind of problem. And one of the ways that I studied it is there was sort of a mental model, a conceptual model, say 15 years ago, about what were the important precursors, say, for secondary organic aerosols. Say things like single ring aromatics, that's the most important. Say precursors, anthropogenic precursors. And the conceptual model was like, oh, that's right. That's if we just study those a little more, we'll figure it out. So one of the things that I've been doing is testing that conceptual model, and the way you test it is not by doing experiments with a single precursor, but you actually take emissions from a real source and photooxidize them and say, well, can you explain what you see with a real source with a single precursor? And it turns out you can't, and so then it's like, well, we're maybe missing precursors. So those are some of the ways that I try to improve the models. So here's some results from some of our work. This is sort of the end of the introduction, then we're going to get into the gasoline. And so this is just looking at secondary. So we're looking at organic aerosol. SOA is organic aerosol that forms in the atmosphere from this atmospheric chemistry, and POA, lots of acronyms, lots of job security, is the directly emitted sort of organic aerosol. And so here for 3 different sources, these are on-road gasoline vehicles, on-road diesel vehicles, and biomass burning. So it's taken us like 5 or 6 years to do this sort of set of experiments. And what you see is for these different sources, we're going to be talking about gasoline vehicles today, and these are fuel emission factors or SOA production factors. These are measured in smog chambers. We'll talk a little bit about smog chambers in a minute. But it's showing you sort of how important sort of secondary organic aerosol production is relative to the primary emissions. And for light-duty gasoline vehicles, it's like 10 times more important on average. They're scattered, but it's a lot more important as measured in the chamber, which isn't an enormous amount of sort of photooxidation. For diesel, they're kind of comparable. And for biomass burning, the emissions are very, very high. And actually, we're getting a little less secondary organic aerosol production than the sort of direct primary emissions. So it seems like light-duty gasoline vehicles, an enormous source of reactive organic gases in urban environments. You get a lot of secondary organic aerosol production, so it seems like a good source to sort of focus on, and that's what we'll be talking on today about. So what have we done? So we've gone in the lab, and we've done a lot of experiments with different vehicles to study the secondary organic aerosol production. So this is a picture of a test cell in Los Angeles at the Hagen Schmidt Laboratory. This is a vehicle that's been recruited from the California News Fleet. It's, you know, you got a little slip in the mail. It said, oh, we'd like to borrow your vehicle for a couple of weeks to do an experiment. You say, oh, sure, and we give you $500, and that's sort of how it works. So these are in-use vehicles, and we run them on the dynamometer. Here's a portable smog chamber. Here's the CBS tunnel. And there's all sorts of instrumentation around here to measure those emissions and study how they evolve in the atmosphere. And the chamber gives us sort of an experimental system where we can take emissions from a car and then study how that sort of evolves, you know, without all the other complexities of what's going on. There's strengths and weaknesses of this sort of approach, but this is what I'll be talking about today. So this is what the experimental setup looks like. So we run a car, light-duty gasoline car, or a light truck, passenger truck, on the chassis dynamometer. We use something called the cold start unified cycle, which is the same as LA92, which is a duty cycle that's been developed to represent driving a typical trip in Southern California. It looks a little bit like the FTP, except it's more aggressive and you have higher emissions. Then it goes into a constant volume sampler. This is a very standard way of sort of characterizing the emissions. It's just a big tube, and they mix the emissions. They take all the emissions from the car, and then they mix it with cleaned air. And then you pull off all sorts of samples off the end to sort of characterize what's being directly emitted. And we had a very large suite of stuff that we were characterizing, and then we push some of those emissions, dilute emissions from the CBS, into a smog chamber. And then we could turn on some UV lights to simulate, you know, the photooxidation that happens, and then study the sort of production of secondary organic aerosol in the chamber. And then we had a whole suite of instruments here that we're measuring off the chamber. And then we can compare with what we knew was going into the chamber and see if we could model it and explain sort of what was going on and understand what we were observing. And we did this with a test fleet. We tested, I think, 84 vehicles. I don't think the numbers here add up to 84 because I didn't have the right numbers, but I think we did 84 total vehicles. 25 we tested in the chamber. So it's a reasonable sized fleet. So it spans a wide range of sort of model years, from vehicles built in the late 80s all the way to vehicles sort of built in 2014. And they were certified at different emission standards. And so pre-LEV is vehicles that didn't meet the sort of initial LEV standard, which came into force in 1994. But you can see a wide range of model years where it's sort of at the pre-LEV level. Then there's a wide range that meet what's called the LEV standard. Then there's the ULEV standard, and then there's the SULEV standard. So there's these different standards, and you'll see as we look at the data, as you go to these vehicles that are certified at more stringent standards, the emissions are much lower, as you would expect, and things like that. So that's what this shows. And so this is just a little bit of primary emissions data. And so each of these, I don't have the numbers of vehicles in each of these categories, but it's on the order of sort of 20. And this is looking at the emissions of non-methane organic gases. So it's a measure of the total organic gas emissions as measured with an FID, sort of integrated over this whole test cycle. And there's lots of interest if you look at, you know, second by second data, but this is just integrated over the whole test cycle. And what it shows is you go from these older vehicles that are certified at a lower emission standard, the emissions are on the order of 10 grams per kilogram fuel. And then, the SULAB, these that meet the most stringent standards, are a couple of orders of magnitude lower. And so this is reflective of, improvements in engine control technologies, improvements in catalytic converters and things like that. This is a dramatic reduction. And I could show up other pollutants and you would see these types of reductions. And one of the questions, right, with the VW sort of crisis is sort of brought up. The VW would look pretty good. We've tested VWs on the dynamometer. Little did we know that they weren't running. So, there is sort of this implicit assumption. It's not like this is exactly how it'll be emitting in the real world, but that this is correlated with how it's emitting in the real world. And as you ratchet down the standards, that the stuff in the real world is going to go down at the same time. So that's another talk. So particle phase emissions, again, just a little bit of primary emissions. Again, so particulate matter. As we move from these, I don't have the sort of super old vehicles. This is the same as ULAB, Lab 2, and this is SULAB. So you can see there's been some reduction here. This is gasoline vehicles. And then you guys have done some work. Naomi did some really nice work around GDIs, gasoline direct injection engines. They have higher emissions, and it's clear here. Lots of other people have shown that as well. And what else do we see? So the current regulation is about 10 milligrams per mile. It's not tested on the unified cycle. It's tested on an easier cycle. And according to all these current regulations, all the vehicles meet that standard, though there's, given that you're so much below it, there's sort of this backsliding that's happening if you go to GDI because of the higher black carbon emissions. But then if you look at the future standards, and these are the standards that are getting rolled out right now in the United States, the Tier 3 standard is a federal standard, and the Lev 3 is the sort of California standard, and you can see that the GDIs are well above that. And this is a more aggressive test cycle than the FTPs, so maybe you give it a factor 2, but even if you give it a factor 2, you're not going to be there. So there's a lot of sort of discussion right now in the automotive community about what to do. Gasoline particulate filters, fuel reformulation, what are we going to do? And they're making a lot of progress, and this is an example here, is so if you look at the SULAB GDIs, which are becoming more spray-guided as opposed to wall-guided. The initial ones were wall-guided, and they're changing the injection technology as the technology matures, and they've definitely made substantial progress in, say, reducing those emissions, but still it's not clear they're going to meet the 1 milligram per mile sort of California standard. So this is just testing. This is, I don't know, probably in 10 SULAB GDIs, which we have lists of what sort of spray and wall-guided. I guess this is getting kind of a little wonky, but I mean, it's a continuum of sort of geometries. And then the other thing is here's just a little bit of composition data, and sort of organic matter is here. This is black carbon is the black, or elemental carbon, and you can see that the GDIs look an awful lot like diesel in terms of they're really sort of black carbon dominated. Even these, historically people have sort of thought that, there's a lot of organic carbon from these vehicles, and even these port fuel injection vehicles are they're even dominated by elemental carbon. Anyway, so I wasn't going to talk too much about the primary emissions, but we want to know what the kind of initial condition is. Well, we also put it in the smog chamber. So that's what's going on right here. So this is when we're kind of injecting into the smog chamber, and the sampling port is probably not that far away from the injection port. So as we're injecting, it's kind of high. And then we have sort of this initial characterization period, and the yellow part is when we turn on the UV lights in the chamber, and that drives photochemistry. And you can see that here is the NO gets, there's some ozone production. The NO goes away as it gets turned into NO2, and you can see that there's this production of secondary organic aerosol that's going on inside the chamber, and you can see there's substantial production of secondary organic aerosol. Primary organic aerosol here is, really low level, half or a quarter microgram per meter cubed, and at the end of the experiment, up around 3. There are two curves here. This is what's actually measured, and then there's loss of material to the walls, and that's a whole other subject is correcting for those sort of wall losses. This is an estimate of what the wall loss is. But clearly, even if you don't wall loss correct, you can see there's still a substantial enhancement in the amount of particle mass that's inside the chamber. So this is what the data look like when you do these smog chamber experiments. The last thing to say is, this, I don't know why we sort of cut it off at 1.5 hours. Usually the experiments run about 3 hours. Most of the chemistry occurs in the first hour or so. And the oxidant levels in the chamber, at least the hydroxyl radical levels are kind of comparable to sort of daytime, summertime conditions. So it's not like this is an experiment on steroids like some flow reactor. So this is kind of what I think of as sort of real-time, daytime types of conditions. So this sort of production. So what do we see? So if we've done this with a lot of different vehicles, and you look at the secondary organic aerosol production, and it looks a little bit like the figures we were looking at before. As we move across to these more stringent classes, we see this reduction in secondary organic aerosol formation. And for the SULABs, we're kind of around the blank level inside our chamber. We can run the chamber just on clean air out of the CBS, and we get a little bit of background SOA production, and we can see something similar for the SULABs. And there was a little bit on the design of the SULAB experiments. We actually had, it was more dilute, so we didn't have quite as high concentration, so our detection limits weren't quite as good. But this is kind of, it's down around the sort of detection limit. So, and so CARD really like this, because they're like, done, solved, no more regulation needed. That's going to get us where we want to be. But we've done some other flow tube experiments, and it's not quite that easy, but anyways. And it sort of mirrors a little bit, the trend in NMOG, right? There's this dramatic reduction in NMOG, and we see this reduction in sort of secondary organic aerosol. So great, super duper. Little aside, we see similar things to the GDI. So there's not big differences between the GDI and the port fuel injected engines. As we get back with LEV, I think we only had one LEV GDI. There are not that many LEV GDIs. There are many more sort of newer ones. So that's just a quick aside. But one troubling thing with what we saw here is, say you look at the data, this, and say, well, we're kind of around the detection limit here. But if you look at the other data, if you look at the reductions in sort of non-methane organic gas emissions, you see that there's this, say, factor of 20 reduction when you go, from pre-lab to ULab. But then if you look at the amount of SOA production, it goes from, it only goes down by about a factor of 4. And you can control for organic aerosol loading. You can control for oxidant exposure and things like that. And it's, this suggests that, these newer vehicles potentially are emitting a little bit more potent mix of precursors. So you're not getting this kind of one-to-one reduction. And so that certainly got the attention of the Air Resources Board, and that's why we went back. They sort of funded another project where we went and looked at a bunch of sort of SULABs in a variety of ways. So they're worried about, well, are they really going to get the reductions in organic aerosol that they wanted to in LA? And this talk is about this trend and what's really going on with this trend. So another way to represent this is talking about this as an effective SOA yield. And so this is essentially the ratio of the mass of the SOA to the mass of reacted precursor. So it's less than 1, generally. I guess it could be with added oxygen or whatever, but it's less than 1. And you could look at the yield and get a sense of sort of how efficient these different precursors are. And what you see is you have this reduction in NMOG, but then you see this increase in sort of SOA yield. And so for the pre-lab vehicles, the yields are sort of on the order of 4 or 5%. So this is 4 or 5% of the reacted organic gases are ending up in the particle phase. But then we look at these newer vehicles, and we see it's more like 40%. It's like, whoa, what's going on? And that's sort of a puzzle. And understanding what's going on here and why is it that they're emitting a different mix of precursors? Is there something else going on? Do we screw up the experiment? It's taken a number of years to figure out what's going on, but the first time ever, this crowd will know what's going on. So anyway, so what's causing this higher yield? And so one hypothesis is that the emissions are just different, and that the changes in catalyst technology, how you run the engine, the emissions have changed enough so you're going to get much more a mixture of stuff. Even though it's lower emitting, the mixture is different. That's going to cause sort of it to be a more effective sort of SOA precursor. So that's one potential hypothesis, and this would be like, oh my gosh, we got to put in different control technology. The other sort of hypothesis is that we screwed up and we didn't have consistent experimental conditions, because the chemistry in the atmosphere, there's a lot of branching, there's a lot of different routes that the chemistry can go, and if you're going different routes with different vehicles, that could cause potentially higher yields, right? There's been SOA experiments that looked at the dependence on NOx, and you can get higher yields at low NOx conditions. And we tried to control for that. But as you'll see, we didn't do such a great job. Anyway, so organic emissions and SOA precursors. So if you look at what's coming out of the tailpipe of a gasoline-powered car, I mean, it's everything from methane to like a C40 alkane. I mean, it's just this huge spectrum of organic material. And gasoline, of course, is sort of centered around kind of octane. So if you look at gas, it looks sort of here. And so we want to think about, this is sort of a space that we use to sort of think about what these emissions are. And one of the reasons it's important to sort of think about this space is not every organic compound can be a secondary organic aerosol sort of precursor. I guess it depends. In these experiments, there's not a lot of aqueous SOA going on. They're pretty dry. So it's really the kind of classical larger hydrocarbons, aromatics that are being oxidized. They form products that are condensable or semi-volatile. So it takes, you can't do that with like propane. You know, you just can't lower its volatility enough as you add an acid group or whatever to make it go into the condensed phase. So you have to be down here. It's really like benzene and for aromatics, you need to get to benzene, but a C6 alkane won't make SOA. So you have to be down in the sort of lower end of the sort of what we call the volatility spectrum to make sort of secondary organic aerosol when it oxidizes. Essentially, you have to be, you take a compound from here, essentially what the chemistry is doing is pushing it down here to have that compound. You have to be down in this part of the space, the partition into the condensed phase. So the chemistry is sort of shifting stuff to the left in this diagram to make secondary organic aerosol. But you have to start far enough to the left to sort of, you get that sort of push. And so there's only a subset of the compounds that are going to make secondary organic aerosol. So we really needed to take those non-methane organic gas emissions and really speciate them, right? We need to know what they are to be able to run them through the model, because we got to throw out propane, right? We got to throw out the light stuff, and we need to apply different yields. Like a C10 alkane will make less SOA than a C14 alkane. So we need to know all that kind of detail. So we did a lot of speciation work. And this is just looking at, say, traditional GC in carbonyl sort of speciation. And we can speciate about 75% of the non-methane organic mass or gases as measured with an FID, and they're broken down into these sort of different sort of categories. And for all these categories, secondary organic aerosol precursors are really just the red. So it's about a quarter of the emissions are these single ring aromatics, and traditionally those are thought to be the most sort of important sort of SOA precursor. But if you look at the diagram, there's a lot of white at the top, and that's because we didn't have mass closure, right? We did a lot of speciation. We speciated like 250 compounds or something, and there still was emissions that were unknown. We could count them with our FID, but when we tried to add up everything that we speciated, there was this gap. And these are data, you know, there's sort of 20 vehicles in each category. So there's a fair bit of data in each category, and there's sort of this sort of systematic bias that was sort of going on. So there's carbon that's coming out that's not speciated. And so this is another thing that I have spent time on. And so a lot of this carbon is what we call IVOCs. So if I jump back here, so the VOCs are really kind of operationally defined as sort of organics with, say, smaller than C12 when you're thinking about sort of hydrocarbons. And they're organics that you can measure with canister samples, you can measure with Tedlar bags, you can measure with traditional GCMS. But as you get to larger compounds, they get stickier, and you can't use those techniques to measure. You have to use sorbents to measure them. And that's when you come into what we call the IVOCs, which are these intermediate volatility organic compounds. They're very effective SOA precursors, but they're harder to measure because they're a bit stickier. Arthur works on measuring these. I work on measuring these. Other people work on measuring these types of compounds. But historically, they haven't been measured as much. And part of that is because a lot of the initial speciation work was driven by ozone chemistry. And it's like, well, maybe that's 20% of the emissions or these low volatility things. We'll assume it behaves the same way as the higher volatility stuff. Oh, and the ozone mechanisms work okay. So we're okay. But for secondary organic aerosol formation, those are very important because they have high yields. And so one of the hypotheses is a bunch of this missing mass is this lower volatility stuff that hadn't been measured very much in gasoline vehicle exhaust. So one of the objectives of our project was to sort of measure that. So how do you do that? So we would collect on sorbent tubes, on 10x tubes, and we'd thermally desorb them into doing GCMS. We also worked with Alec Goldstein at UC Berkeley. He did GCGC, UV-Vis, blah, blah, fancy sort of characterization. So we're going to sort of walk through some of that kind of characterization work, show what we saw, which is normally measured, and then put it back in the mass balance and kind of see how we're doing. So what do we see? Well, this is what we see when you thermally desorb something like one of these samples, and this is sort of the IVOC range. And so there's a bunch of peaks, so there's individual compounds you can identify, but there's this enormous amount of blah that's sort of coming out, which are all these isomers that aren't sort of separated cleanly in one-dimensional GC and sort of electron impact ionization. So there's a lot of UCM, unresolved complex mixture, which is a common thing when you're sort of looking at these sort of hydrocarbon mixtures, and it becomes more of a problem as you get to larger carbon numbers because the number of isomers sort of explodes. And so there's a bunch of stuff that we can't see. So, but this is there, it's in the chamber, it's reacting, and it's probably forming SOA, so we better characterize it and get it represented in models. So what did we do? Well, you can bin it by boiling point number. You have a sort of a boiling point column. You can sort of bin it by sort of carbon size. It's not perfect. It's sort of a functional definition, and you can put it into something what we call the volatility basis set and things like that. But so we're quantifying the mass and representing it in the model, and I can get into the sorts of details. You can also look at the mass spectral signature of it, and there's a lot of aromatic signature here, and we'll look a little more detail of what kind of aromatics they are. And this is sort of after trimethylbenzene and these sorts of things are eluting. It's what I call hairy aromatics. Aromatics with lots of blah, blah, go off to the sides. But you can see just in our simple, sort of not super fancy GC-MS. We'll look at some super fancy stuff now. So this is the same sort of thing. We thermally desorb, and it goes through a 2D GC, and Arthur can talk a lot more about how this works. There's like a polarity column, and then there's a boiling point column. And then this is done by UC Berkeley, and Alan Goldstein and Greg Drodes was the one who did the work. And then they are up at this advanced light source, which is like this $500 million sort of ionization source, pretty cool. And they can photoionize the stuff coming out of the column, and so there's much less fragmentation. So you get a lot more paranions, and you can sort of see what stuff is. Did I mangle it too much, or am I pretty close?
You're doing a great job.
So anyway, so they did it, and they can look and get a much more sense. So we get this sort of really fragmented electron impact ionization sort of mass spectra, and it's like, aromatics all over the place. But this, they can really look at it in more detail. So that's what they see. So here's one of these 2D GC columns. It's like, a terabyte of data every hour or something crazy. It takes like, 10 years of a graduate student to analyze this, and it's only half analyzed. So the alkanes are here. Here are the sort of benzenoid compounds, and then sort of the pHs are here. But there's a lot of stuff there, and we can go in and probe it and sort of see what that stuff is, both as a function of volatility as well as sort of polarity. So anyways, this is sort of getting above my pay grade, but you can look at the fragmentation patterns and sort of make some stuff up and figure out what it is. Chemists do this. I'm not a chemist. That's why Alan Goldstein did it. And Greg. Anyway, so what do they see? It's like, whoa! So they could take this stuff that we were just calling aromatic and say, well, what types of aromatic is it? And so they've got these different, this is my hairy aromatics, right? We got these little blah, blah, off the edge. And so these are for different vehicles, a hot start and cold start. I mean, so what it is, it's like, oh, well, there's a lot of aromatics. We have a much better idea of what it is now. We don't know exactly because there are these various fragments that are hanging off. We don't necessarily know how many carbons are in that alkyl group, but they've sort of classified. And there's not a lot of data for these types of compounds if we're looking at sort of secondary organic aerosol formation. You can't sort of call up Sigma Aldrich and say, oh, can I have that compound? And you got to get in there and synthesize it or something like that. Or at least that's my sort of understanding. So anyway, so there's a lot of really cool data here about what this is, and this additional sort of speciation has sort of provided insight into these compounds, but it's clear these things are going to make secondary organic aerosol, and it's clear they're not in the existing inventory. And so that's one thing that we need to fix. So how much is there? So no mass closure, that's a real bummer. So this is sort of a scatter plot of the intermediate volatility compounds against the non-methane organic gas. You see that they're pretty well correlated except the red points, which are the hot cycles. And you can see that the slope of it says that about 4 or 5% of the non-methane organic gas emissions are these intermediate volatility compounds. But remember I said that 25% wasn't explained. So we're not closing the mass balance. We're still missing sort of 20% of the mass. That's a big bummer. I don't know what that is, I'll hypothesize, but it closes it down. You're like, oh, Alan, that doesn't matter. It's this little scooch of stuff. Remember, this is pretty potent SOA precursor, so that scooch matters because you'd have to sort of renormalize it by sort of yields. And this is sort of thinking about it in terms of primary organic aerosol. So we've tried to make some progress. It was quite disappointing that we didn't make more progress in terms of sort of closing the sort of mass balance. So what do we think what's going on? I mean, one sort of hypothesis, if you look at these lower volatility stuff, there's a lot of gray sort of UCM here, and the red and the blue are various classes of compound. You look at the VOC data, CARB did this work. I think there's a lot of signal there. I mean, they have this target list of compounds. The question is how much additional carbon is sort of in this range that they're not quantifying, with the sort of GCFID. They're too low of a signal. So I think there's a bunch of that that's going on. It's not clear that's a lot of SOA precursor. We're sort of working with that sort of assumption. That we're probably getting most of the sort of SOA precursors, but that's a hypothesis right now. But that's something that needs to be sort of worked on to try to better close the mass balance. Whoops. So if you look at this, and you look at, say, these precursors, if you look at them, I mean, the non-methane organic gases are going down, the single ring aromatics are going down, the IVOCs are going down, not quite as much, The SVOCs are going down, not quite as much. I mean, so there's a little enrichment in these classes, but not crazy enrichment. And so is there something else that we're missing here? Is there something really different about these vehicles, these SULEVs and ULEVs? For what we can see, we don't see any systematic differences. And so it's hard to believe that the composition is so different that it's going to cause this really fundamental difference in secondary organic aerosol formation. So if we take what we think are the precursors, throw them into a little simple model and calculate an effective SOA yield, and this is just some job security up here where we're taking a parent hydrocarbon and we're reacting in a way with its rate constant and assuming an OH constant, and then we're looking up a yield for that compound in the literature. So calculating sort of an effective SOA yield for all of our stuff. And it's saying, well, if we measured all the stuff, we should be able to explain that sort of trend that we saw in the data. And so you can take that, you can take this information, throw it through that little model. The model is that's claiming too much, I mean, a little equation. And you get sort of a calculation of effective SOA yields, and we're getting things from like sort of 9% up to like 15%. This is using sort of low NOx, high NOx yields, because we thought we were doing all the experiments at high NOx. We adjusted carefully the VOC to NOx. And what you can see is there's some enhancement as we go from sort of pre-LEV to SULEV based on this sort of analysis, but the enhancement's less than a factor of 2 versus the kind of factor of 10 that we were seeing sort of in the data. And so there is some enrichment of the sort of lower volatility stuff, but not nearly enough to explain. So maybe there's something in that residual mass, you know, there's super precursor in SULEV or ULEV vehicle exhaust and not in the sort of unidentified pre-LEV. It's not clear to me that that's sort of the case. So basically, when you compare the sort of model predictions based on the sort of laborious, painful speciation, we're just not getting what we're seeing here. So there's lots of places, maybe the speciation is not good, maybe the sort of chamber data for the yields that we're using aren't good. But anyways, I don't think those uncertainties are big enough to sort of explain what's going on. So I would cross this off. So this is what we're arguing, is that the emissions look pretty similar. They go down. There's not a lot of evidence that they're fundamentally different between these sort of different vehicles. I think the fact that there's a little bit more unspeciated for the lower emitting vehicles is just we're kind of running into the sort of detection limit sort of world. So let's look at the NOx effect and whether or not the NOx effect can explain sort of what's going on here. So what's going on here? So this is some atmospheric chemistry, and essentially you oxidize one of these hydrocarbons and it goes down, it makes an RO2, and the RO2 is kind of looking around. And it's going to go down, it's going to react with NO, or is it going to react with HO2? So that's, if it's low NOx chemistry, it's going to go down and react with HO2 or another RO2, or with a high NOx chemistry, there's NO floating around and it's going to go down that sort of path. And so you get different products. When you do that, you get different products, and the volatilities of these products are different, and the amount of SOA that they form is different. So if you're going, depending on which of these branches you're going down, you can form different amounts of SOA, and this has been demonstrated in the laboratory. So this is the high NOx regime where there's lots of NO floating around. You can go down this sort of path, and when there's not much NOx, you go down that sort of path. And this has been, oh, I took out that slide. Bummer. But this has been studied for single ring aromatics and a few other compounds. And say for single ring aromatics, the yields at low NOx conditions are 4 or 5 times higher than they are at high NOx conditions. But for alkanes, large alkanes, they're about the same. So it's compound dependent. And people who know more chemistry than me can start arguing, like Paul Zeman or something like that, can start explaining what those differences are. But there are these sort of differences. The problem is we don't, I don't know if we've got all the precursors measured. Only, of the anthropogenic precursors, only a handful of the NOx effects have really been studied in the laboratory, so there's not a lot of data to sort of look at this. So we're going to look at it empirically. We're going to take the data. So one of the things that happened, if you look at our experiments, so here's the effective SOA yield. We've seen this, and now this is looking at the initial sort of non-methane organic gas, the NOx ratio, parts per billion carbon to parts per billion NOx. And we had tried to control this. We actually had added propene to the chamber. We adjusted it, but we had added HONO to the chamber to help, photolize the HONO to make hydroxyl radical. And we're using a chemiluminescent NOx monitor. Ugh. So the HONO gets measured as NOx. Oh. Pretty stupid, but anyway, so the net effect was we had a pretty strong dependence. And if you actually look at the data, and bin the data, you sort of plot it this way, there's a very strong sort of NOx dependence. yields. And you look at the effective yields that were started calculating, we had it by sort of vehicle class, and it seems like there's a very strong sort of NOx dependence. And this is consistent with aromatics being the sort of dominant sort of precursor, and there being a very strong sort of NOx dependence for aromatics on SOA formation. So some models have some representation of this in it. It's okay, but not sort of strongly. And so now I want to argue that this is potentially a really big deal if you are worried about air quality in Los Angeles. So what's going on in Los Angeles? So we're busy implementing LEV 3, and people are buying these new SULEV vehicles, and what's going on is the emissions from light-duty gasoline vehicles are going down. And so this is the Air Resources Board projection of the emissions normalized to 2014 or whatever, and they're predicting by 2035 that the emissions, not NLOG emissions from light-duty gasoline vehicles, are going to go down by 80%. So we're like, great, our SOA from light-duty gasoline vehicles is going to go down by 80%. Yahoo! That's awesome. But there's a lot of pressure right now to reduce NOx for ozone. And so there's really strict NOx controls also being implemented in Los Angeles at the same time. So if you look at the predictions of the change in the VOC to NOx ratio in LA, this is sort of an average, and it's different on weekdays and weekends, it's different during time of the day, is that the non-methane, the VOC to NOx ratio is going to shift from about, basically from the high NOx regime into the low NOx regime. So we're sort of shifting over this sort of steep part of the curve. So then you take on this effective SOA yield that we sort of measured in the laboratory, and so right now we're sort of shifting over the next 2 decades from here to here, and so that's like where there's a big change. And you put all the stuff together, and if you believe the data from light-duty gasoline vehicles, we may not have any reduction in the amount of SOA that's produced from these vehicles because the atmosphere is changing and the effective yields are going to go up. And so our data, you take this prediction with what we measured empirically in the laboratory, you get something like this. And even the amount of secondary organic aerosol from light-duty gasoline vehicles could actually go up. And then even when it's gone down so much, and that's because the effective yields have been increased if this NOx dependent is sort of true. And so this is for light-duty gasoline vehicles. There's certainly other sources. This isn't the only source. It's a big source of non-methane organic gases in the Los Angeles basin. There's NOx dependence for biogenics and things like that. And so again, I guess the idea here is this was a conundrum that we sort of have. We think it's actually a NOx effect and not sort of a difference in precursor effect. And if you read my paper or our papers from 3 or 4 years ago, we're like, man, what's up with these LEV 2 vehicles? But we really think it was sort of an experimental design problem. And it may, in some ways, I think it sort of turned out fortuitous in terms of sort of seeing what's going on. But that's all I got to say. And so that's kind of what we're thinking about. And so basically the bottom line is there's a lot of secondary aerosol production from light-duty gasoline vehicle exhaust. Light-duty gasoline vehicles are getting a lot cleaner, but the sort of chemistry of the atmosphere is shifting. As we shift from a low NOx to a high NOx regime, that has a lot of implication in terms of the effectiveness of potentially these sort of control strategies. So we need to think about this stuff in a bit more integrated way. Be happy to take any questions.
Any questions? It's a lot to take in. Yeah.
John?
I mean, it's almost impossible to believe that you can do a direct emissions from an engine into a bag and be in the low NOx world.
Yeah.
But I guess that's what you're saying. But just a technical question. Like you're reducing the VOC levels so low. Is it possible that the OH concentrations in the bag are different from with the SULEVs to the more polluting?
And they are.
And so you're pushing the oxidation further and forming more.
And you definitely are.
Organic.
So that is going on as well. And so so when you just compare the production rates, that's embedded in the production rates. And there's also there's more OH for the cleaner vehicles, right? Because the burden in the chamber is lower.